Okay, welcome all to participate in the SAVNet working group. So it's time to begin our meeting. So first, I will introduce the status of our working group. As planned, we just want to finish the adoption call for the problem statement, but there are some comment and objection for the previous discussion. So the author of the two draft have responded the comment and updated the document. So in this meeting, we want to focus on the update of that and try to solve the comment for the two draft. Currently, there are already 12 documents for our working group. So after the discussion of the problem statement and architecture document, we will discuss, introduce the other solution for the document. So as I said, the goal of this meeting is focus on the discussion of the problem statement and the requirement and gap analysis draft. So the chair and want to make sure that after the meeting we want to get the conclusion. So the question want to ask the working group is whether this update draft is good enough to be adopted by the working group. So the other content from the audition draft will be considered aligned with the about for document later. So this is the draft agenda for this meeting. We will pay about 80 minutes for the papers for document, and after that we will discuss the additional solution for our for the additional document. Okay, so that's all. So I change the slide. So if there is no any problem for the draft agenda, we can begin the first document for the gap analysis for the intro domain.
Have the presentation, just tell us when to move to the next slide. Okay.
Yeah.
Okay. Good morning, everyone. I'm Dan Li from Tsinghua University. So for many colleagues in this Zoom, actually we have met for several times before online, but this may be the first time we meet in person. So before my presentation, I want to express my sincerest thanks to every one of you who have made great contributions to this SAVNet working group. Thank you very much. So today I will just present the gap analysis, problem statement, and the requirements for source address validation in intra-domain networks. Next. For this draft, we just perform the gap analysis of existing intra-domain solve mechanisms, summarize the fundamental problems of existing intra-domain solve mechanisms, and describe the requirements for new intra-domain solve mechanisms. We have already made actually 8 historical versions for this draft. We presented the 0.0 version in IETF114, the 0.03 version in IETF115 last time. And after that, we received a lot of comments and feedback in the IETF meeting as well as in the mailing list. So we again made several rounds of revisions, and the current version is 0.7. Next. And so since last IETF meeting, we just summarized the representative comments from our colleagues. For example, Barry just said that maybe we should include more access network solve mechanisms such as DocSys tool, TR69, and FTTH tools, as well as the DHCP source verifier tools, these kind of things in the introduction section. Actually, all of these technologies are for access networks solve tools. They are not the main focus for this SAVNet working group, but for better description of existing work, we also include this part in the current latest version. And Roland and Dobbin just said that should we focus on interdomain instead of intradomain? Actually, both intradomain and interdomain solve are the scope of the SAVNet working group. And in the latest version, we just describe the boundary between interdomain and interdomain solve and explicitly show what's the difference. And answering asked why we removed the part of misaligned incentive from interdomain draft. Actually, in the initial version of this draft, we have the incentive part, but actually incentive is actually also a technical problem, which just answer the question that how the deployed AS can benefit from the deployment of solve mechanisms. But maybe that's more about the focus of interdomain solve. So in the current versions, we just removed the incentive part from the intradomain solve problem statement. And for the interdomain draft, we also removed that while put the incentive problem to an individual part because actually from technical perspective, actually I think maybe an individual draft is better. Next. And Jared actually asked several questions. First is that Jerry just cared about the cost we have to pay for solve. Maybe solve will break more things that it can prevent. Actually, Jerry also concerned that the largest attack today doesn't come from spoofed packets. We think that solve is still very important for identifying and preventing various spoofing-based attacks. And this is also the concerns of ISOC, CADA, something like that, all these kind of projects in our community. And in recent years, the DDoS reports published by NetScout and Cloudflare have also indicated that a significant proportion of DDoS attacks are based on source address spoofing. And okay, Jerry also asked that there are maybe completely impossible things such as the entirety of section 3.2, which must be striking in order to have a point to start with. We think that this problem is worth of more discussion. And the updated draft, we just reframe the requirement section to put requirements as, okay, which can be fully fulfilled or partially fulfilled when designing new interdomain solve mechanisms. And Jerry also have some concerns about the performance degradation by introducing solve. Actually, in last IETF meeting, H3C actually company, they just made experiment to show the performance of introducing solve mechanism in routers. I think that's a good starting point to study the performance of solve rules, solve tables in the data plane. Next. Okay, so compared to the version 0.3 we presented in last IETF meeting, in the latest version, we just made the following updates. First is we made updates in the introduction section by introducing access level solve mechanisms, as well as explicitly identify the goals of interdomain solve mechanisms. Next. So in AFC 5210, actually the Sava architecture just divides solve into 3 check-in levels. That is access level solve, intradomain solve, and interdomain solve. So for access network level, we just ensure that a host uses a legitimate source IP address. There are a lot of actually tools, methodologies for achieving this kind of host level source address validation, such as static ACR, dynamic ACR, like radius and diameter, like SAVI solution for DHCP, IP source guard, keyboard source verify, this kind of technologies. They are not the main focus of the SAVNet working group, because the SAVNet working group focuses on intra-domain network and inter-domain network. But we actually also include all these access network SAV mechanisms in the current version. And we know that the motivation of this working group is that access network SAV is not enough, because we cannot require that all the access networks deploy SAV around the world, because the number of access networks is so huge. So when some access networks do not deploy SAV, intra-domain and inter-domain SAV and routers can help check the spoofing traffic as close to the source as possible. And that's the main focus of this working group. In other words, we just focus on IP prefix level instead of IP address level SAV. Next. So we may just ask that, okay, what's the boundary and what's the difference between intra-domain and inter-domain SAV mechanisms in this SAVNet working group? So in this latest version, we just explicitly made the definition. For intra-domain SAV mechanisms, we just care about the scenario where ASX defends against the source address spoofing without the collaboration of other ASs. In other words, without the information learned from other ASs. For example, okay, we can just prevent the outgoing traffic originated from a subnet of ASX from spoofing the addresses of other sublets. Or we can prevent the incoming traffic to ASX from spoofing the addresses of ASX. For this kind of scenarios, actually, an AS can make this solve independently by itself without learning information from other ASs. While for inter-domain SAV mechanisms, we just carry this scenario where multiple ASs collaborate with each other for defending against the source address spoofing. In other words, we need to learn information from other ASs, and these ASs need to exchange information with each other. For example, an intermediate ASX can help defend against the spoofing traffic originated from SA, which spoofs the addresses of SB. Although the originated traffic and the destination traffic are not the ASX, but the traffic goes through ASX, the ASX can help defend the source address spoofing. So, for intra-domain SAV mechanisms presented in this draft, we just carry the two scenarios. First is the outbound traffic validation. That is to block the illegitimate packets originated from the local sublets of SX, which spoof the addresses of other sublets. These sublets may be either within the AS or other ASs. For example, as shown in this figure, for SX, if sublet 2 of SX sends packets which spoof the addresses of sublet 1, which is a sublet of SX, or spoof the addresses of sublet 3, which is a sublet of another AS, actually SX can use intra-domain SAV mechanisms to filter this kind of spoofing packets. Next. And another scenario is for inbound traffic validation. That is to block the illegitimate packets coming from other ASs, which spoof the source addresses of SX itself. For example, SX receives incoming packets which spoof SX addresses from SY. Then, the boundary router of SX actually can check this traffic and finding that these addresses are the internal addresses. It should not receive this kind of packets from outside the AS. Then it can filter this kind of spoofing traffic. So for these kind of scenarios, ASX can make the filtering just based on the information within the AS itself, without the information exchange with other ASs. So that's the focus of intra-domain SAV. Next. This is the updates in the introduction section. And we also add a new section to summarize the existing SAV mechanisms for intra-domain network. This is also the suggestion from our community. we just add more details about analyzing the existing intra-domain solve mechanisms. Next. For intra-domain solve mechanisms, actually the existing tools include the ACL-based solve, which is defined in RFC 2827 and RFC 3704, as well as strict ERPF, loose ERPF, which defining also in RFC 3704, as well as a carrier grid and NAT. Next. So for ACL-based solve, its working principle is that we can configure the ACL rules in routers to block or permit packets which specify the source addresses. And the ACL-based solve mechanisms can work for both outbound traffic validation and inbound traffic validation. For outbound traffic validation, it is usually applied under the downstream interfaces of edge routers connecting the subnets or under the downstream interfaces of aggregation routers. For inbound traffic validation, they are usually applied at the upstream interface of routers, which connect the other ASs. And in any application scenario, the problem of ACL rules is that we should make a manual update in time to be consistent with the latest filtering criteria. That's the main problem. Next. And for strict URPF, its working principle is that the packet is permitted only when two conditions are satisfied. The first is that the local FIB contains a prefix encompassing the packet source address. And the second is that the corresponding outgoing interface for the prefix in the FIB exactly matches the packet's incoming interface. So strict URPF usually works for outbound traffic validation and usually applied under the downstream interfaces of edge routers connecting local subnets. The problem of strict URPF is that it can generate its advantage is that it can generate and update solve rules automatically. But the disadvantage is that it has serious improper block problem in the scenario of asymmetric routing. Next. And for loose ERPF, its working principle is that the packet is permitted if the local FIB contains a prefix encompassing the packet source address. So it usually works for inbound traffic validation, and it is usually applied at upstream interfaces of routers connecting other ASs. Loose ERPF can also generate and update solve rules automatically, but most spoofing packets will be improperly permitted because it is too loose. Next. So for carrier grid NAT, actually it's not an anti-spoofing tool. It is just really for address translation, which manipulates the source addresses and the NAT devices. Next. We also made updates in the gap analysis section, by identifying, the validation of outbound traffic and inbound traffic. Next. For outbound traffic, actually, we made this presentation for several times before. The problem is that when the subnet, has asymmetric routing, actually, there may be improper block problem. Next. Well, for inbound traffic validation, usually we just work under the boundary routers connecting other ASs. The problem is that if we apply ACL-based solve, we just have to do manual update, when the internal prefixes or network topology change dynamically. And if applying loose ERPF, there is a large amount of improper permit. Next. We also made updates in the problem statement section to just summarize the fundamental problem of each of these intra-domain solve mechanisms. For ACL-based solve, its problem is the high operational overhead. As we said, that it requires manual update. For strict URPF, its problem is that there will be improper block under asymmetric routing. And the reason is that it conducts solve based on local FIB, which may not match the real data plane forwarding path. And the problem of loose URPF is that there is a lot of improper permit. Next. We also made updates in the requirement section, by adding the requirements of working in incremental partial deployment. Next. So in the requirement section, we just made the 3 requirements. The first is that the intra-domain solve mechanism should support automatic update without relying on manual update. The second requirement is that the mechanism must improve the validation accuracy, which means that we should avoid improper block under asymmetrical routing. It means that we must include the real forwarding path in the data plane. We also need to reduce the improper permit as much as possible. It means that by including the real forwarding path in the data plane, we should also minimize the set of permittable paths. And the third requirement is that we should support incremental deployment. Okay, we just want to express our acknowledgement to many colleagues in our community. Yeah, thank you.
So we can leave some extra time for the question if there are any questions. Okay.
Put yourself on the queue using the tool first, and then walk to the microphone, please. We manage it with the queue. So Xingkang is first, but anybody else who wishes to speak should go ahead. So I'm sorry I'm mispronouncing your name, but go ahead.
Yeah. Xiangqin, can I begin the question?
Is that me? I'm not sure. Is that me? Can you hear me?
Yeah, we can hear it clearly.
Thank you. Thank you. I'm from H3C. Thank you for giving me the opportunity to speak. Here, I'm willing to share some of my understanding. Firstly, indeed, from a security perspective, the earlier the source address verification is performed in the network, the better. Ideally, this would happen in the access network. However, as we get closer to the user, the number of the devices involved increases, and the administrators of the access networks vary. Therefore, it is hard to require all access networks to effectively deploy SAV. As a result, it is necessary to design SAV tools for different network levels, including intra-domain SAV tools and inter-domain SAV tools. Secondly, for convenience sake, existing SAV tags often directly use routing information that gets forwarding. This routing information focuses on the device interface to reach the user, not the incoming interface for user. This fundamental difference can lead to incorrect source address tags. Therefore, it is necessary to improve the existing mechanisms. Lastly, in my opinion, achieving 100% security is not possible, but continuous improvement can lead to fewer vulnerabilities and a more secure network. Therefore, the problems identified by this draft will contribute to improving network security. That's my understanding. Thank you.
Okay, thank you. We see as an operator, we think the main problem for the SAV mechanism is there is no automatic deployment mechanism, and the accuracy of the existing SAV mechanism is not very high. So we are also looking for the new solution for the problem. Okay.
Okay, thank you very much.
So, okay, if there is no problem, we will make the second presentation.
Please I'm trying to note things in the notepad for minutes, but I'm chairing. I need folks taking minutes. It's designed, everybody can enter things. We just need folks entering who commented, what the topic was, what the general response was. You can see the examples I've already put in. I need other people helping with the minutes, please.
Okay, let's get started. Hello everyone. I'm Li Bin Liu from Zhongguancun Laboratory. I will present the updated version of gap analysis problem statement and the requirements for source address validation in interdomain networks. Next slide. The goal of this draft is to perform the gap analysis of existing interdomain sound mechanisms, summarize their fundamental problems, and describe the requirements for the new interdomain sound mechanism. In the last IETF meeting, we had presented the fourth version, version 3. Based on the feedbacks from the meeting and the comments in the mailing list, we made 4 rounds of revisions, and I will present the latest version, version 7. Next slide. Thank you very much for the valuable comments from the people of our community. We make a summary of the comments and our corresponding response. We have revised the draft according to the comments. And we also put the comments and our corresponding response on GitHub and advertise the GitHub link in the mailing list. Next slide, please. These are the comments and our corresponding response. Next slide, please. Next slide. Okay. We summarize the updates of the draft based on the comments. There are 5 updates of the draft, and compared to version 3, the first updates are in introduction section. We explain the boundary between interdomain and interdomain sound mechanisms, as well as the goal of interdomain sound mechanism. Next slide. The boundary between intradomain and interdomain sound mechanisms. When deploying intradomain sound mechanisms, IIS can defend against the source address spoofing without the collaboration of other AIS. On the one hand, IIS can prevent its subnet from spoofing the addresses or other subnets, either within the AIS or other AIS. On the other hand, IIS can prevent the incoming traffic to it from spoofing the addresses or itself. When deploying interdomain sound mechanisms, multiple AIS collaborate with each other for defending against source address spoofing. In other words, ASX helps defend against spoofing traffic originated from ASA, which spoofs the source addresses of ASB. Next slide. We use an example to illustrate the interdomain sound mechanisms. There are 4 AS in the figure. P1 is a source prefix of AS1, and P3 is a source prefix of AS3. Both AS1 and AS2 deploy intradomain sound and interdomain sound. AS3 and AS4 deploy neither intradomain nor interdomain sound. AS4 sends the spoofed traffic with source address in P1 and destination address in P3 to S3 through AS2. Next slide. In this scenario, intradomain sound cannot help defend against spoofing traffic. S4 does not deploy intradomain sound, so it cannot block the spoofing traffic. Although AS1 deploys intradomain sound, the spoofing traffic from AS4 to S3 do not go through AS1, so the spoofing traffic cannot be blocked by AS1. Interdomain sound can interdomain sound can help in this scenario. Since S1 and S2 deploy interdomain sound, S2 knows the correct incoming interface or packets with P1 as source addresses, and the spoofing packets can be blocked by S2 since they come from the incorrect interface. Next slide. The second major update is that one new existing interdomain sound mechanism section is added. Next slide. This slide summarizes existing interdomain sound mechanisms: ACL-based sound, URPF-based sound mechanisms, source-based remote triggered black hole filtering, carrier-grade net, and BGP origin validation. Next slide. ACL-based sound is a technique that relies on ACL rules to filter packets based on their source addresses. It can be deployed at provider interfaces, customer interfaces, or peer interfaces, and it is recommended to deploy at provider interfaces or customer interfaces. At customer interfaces, it can block source address, source prefix that are clearly invalid in the inter-domain routing scenario, such as sub-allocated or internal-only prefix or customer AS. At customer interfaces, it can prevent customer ASs from spoofing source addresses or other AS that are not reachable via the provider AS. And also, it can be implemented at border routers or aggregation routers if border ACLs are not feasible. However, ACL rules need to be updated in a timely manner when prefix or routing OS change, which relies on manual configuration. Next slide. Strict URPF is the most stringent mode of URPF-based mechanism and only permits packets that have a source address that is covered by a prefix in the FIB and that the next hop for that prefix is the same as the incoming interface. And it is recommended for deployment at customer interface that directly connect to an AS with sub-allocated address space to prevent spoofing attacks from that AS or its downstream AS. Next slide. Loose URPF verifies the source addresses of the packet by matching it with one or more prefixes in the FIB, regardless of which interfaces the packet arrives at. If the source address is not reachable, it discards the packet. And it is typically deployed at provider interfaces or IS to block the packets with source addresses that are previously disallowed, such as non-global prefix. Next slide. FPURPF maintains a reverse path forwarding list, which contains a prefix and all their permissible routes, including the optimal and alternative ones. It permits a packet only if the packet's source address is encompassed in the prefix of the RPF list, and its incoming interface is included in the permissible routes of the corresponding prefix. And it is recommended to be deployed at customer interfaces or peer interfaces, especially those that are connected to a multi-homed customer AS. Next slide. VRF URPF uses a separate virtual routing and forwarding table for each external BGP peer and checks the source address or incoming packet from an external BGP peer against the VRF table for that peer. If the source address matches one of the prefixes in the VRF table, it allows the packet to pass. Otherwise, it drops the packet. A VRF table can be used as a way to implement BCP 3.8. However, the operational feasibility has not been proven. Next slide. EFP-URPF consists of two algorithms, algorithm A and algorithm B. It is based on the idea that an AS can receive BGP updates for multiple prefixes that have the same origin AS at different interfaces. EFP-URPF allows a packet with the source addresses in any of those prefixes to pass on any of those interfaces. It can be deployed at customer interfaces or peer interfaces or IS. It is not implemented in practical networks yet, but BCP 8.4 suggests using EFP-URPF with algorithm B at customer interfaces. Next slide. A source-based RTBH filtering enables the targeted dropping of traffic by specifying particular source addresses or the address ranges. It uses URPF, usually loose URPF, to check the source addresses on incoming packet against the FIB. If the source address of the packet does not match or is not covered by any prefix in the FIB, or if the route for that prefix points to a black hole, it discards the packet. It can filter out attack traffic at specific devices, such as AS border routers. Next slide. A carrier-grade NAT is a technique used by service providers to translate between private and public IPv4 addresses within their network. It enables service providers to assign private IPv4 addresses to their customer AS instead of public, globally unique IPv4 addresses. It has operations on source addresses. However, it cannot determine whether the source address on an incoming packet is spoofed or not. Additional sound mechanisms need to be implemented. Next slide. BGP origin validation. Attackers can bypass URPF-based solve mechanism by using prefix hijacking in combination with source address spoofing. To protect against this type of attack, a combination of BGP origin validation and URPF-based mechanism is recommended. For BGP origin validation, BGP routers can use ROA information, which is a validated list of prefix maximum length origin AS to mitigate the risk of prefix hijacks in advertised routes. Next slide. The third major updates are in gap analysis section. We perform the gap analysis of existing inter-domain mechanisms for sale at provider interfaces, customer interfaces, or peer interfaces. Next slide. For sale at provider interfaces, ACL-based sale, source-based RTP filtering, or loose URPF can be deployed. This slide shows a scenario of the reflection attack from provider AS. There are 4 AS, both AS1 and AS4 have deployed SAO, other AS do not. SAO at AS4 is considered facing AS3. An attacker which is instead of AS3 or connected to AS3 through other AS spoofed traffic with source address in P1 and destination address in P2. As shown by the red arrow, the green arrow shows the legitimate traffic. Next slide. When deploying ACL-based SAO or the source-based RTPH filtering at S4, operators need to perform timely update of ACL rules or the specified source addresses based on the prefix or topology changes of S1 and S2 in this scenario, which incurs high operational overhead. Next slide. When S4 with loose URPF would improperly permit the spoofed traffic, since S4 with loose URPF cannot determine whether legitimate traffic with source address in P1 will come from S1 or S3. Next slide. For SAO at customer interfaces, ACL-based SAO, source-based RTPH filtering, strict UPF, FPURPF, VRFURPF, or EFPURPF can be deployed. This slide shows a scenario of limited propagation of prefix caused by no export. S1 adds no export in BGP update to AS2, and S1 selects the S1 to 3 as the best path to P4. Next slide. Both ACL-based SAO and source-based RTP filtering have operational overhead like performing SAO at provider interfaces. Assuming S3 is a customer AS4, strict URPF, FPURPF, VRFURPF, and EFPURPF with algorithm A would improperly block the legitimate traffic with source address in P1 in this scenario. And EFPURPF with algorithm B works well. However, assuming AS3 is a lateral peer of S4, this strict URPF, FPURPF, VRFURPF, EFPURPF with algorithm A or B would improperly block the legitimate traffic with source address in P1. Next slide. This slide shows another scenario for SAO at customer interfaces, a direct server return scenario. P3 is not advertised by AS2 through BGP. When deploying strict URPF, FPURPF, VRFURPF, or EFPURPF at S4, S4 would improperly block the legitimate traffic with source address in P3. Next slide. For SAO at peer interfaces, both ACL-based SAO and source-based RTP filtering have the same operational overhead as performing SAO at customer interfaces or customer interfaces or provider interfaces. FPURPF, VRFURPF, or EFPURPF may improperly block the legitimate traffic in cases of limited propagation or prefix or hidden prefix, such as DSR, like performing SAO at customer interfaces. Next slide. Besides, for SAO at peer interfaces, this slide shows another scenario of the reflection attack from peer AS. When deploying EFPURPF with algorithm B, at the customer interfaces and peer interfaces or S4. S4 would improperly permit spoofed traffic with source address in P1. Next slide. The fourth major updates are in problem statement section. We remove the subsection of misaligned incentive, and we summarize the problem for each interdomain sound mechanism. Next slide. ACL-based sound and source-based RTPH filtering may have operational overhead, as operators need to manually update ACL rules or the specified source addresses to adapt to network changes. Strict URPF may have improper block problems when it's in multi-homed and has asymmetric routes, as it performs some only based on the local FIP, which may not include asymmetric routes or legitimate traffic. Next slide. Loose URPF may have improper bit problems, as it is oblivious to the incoming interfaces or packets. FP URPF and VF URPF may have improper block problems in asymmetric routing scenarios, such as limited propagation of prefix, as they perform some based on the local RIP, which may not have the prefix with limited propagation, and they are permissible incoming interfaces. EFP URPF may have improper block problems in the cases of hidden prefix, as it cannot learn the legitimate source prefix in such case. Next slide. The last major updates are in requirements section. We remove the subsection of direct incentive and acceptable overhead, add the subsection of automatic update, and revise the description of requirements. Next slide. Based on the gap analysis and problem statement, we get requirements for the new interdomain sound mechanisms. First, automatic update. The new interdomain sound mechanism must be able to adapt to dynamic networks and asymmetric routing scenarios automatically, instead of relying on manual update. Second, accurate validation. The new interdomain sound mechanism should improve the validation accuracy in all directions OS over existing mechanisms. It should avoid improper block and minimize improper permit by learning the real forwarding path, or the minimal set or acceptable paths that cover the real forwarding path. Multiple sources of sound-related information can help reduce the set or acceptable paths and improve the validation accuracy. Third, it should work in incremental or partial deployment. The new interdomain sound mechanism should provide effective protection for source addresses when it is partially deployed in the internet. Next slide. So these requirements serve as the practical guidelines that can be met in part or in full by proposing new techniques. Next slide. Many thanks to the people from our community for their valuable comments on this document. Thank you very much.
Yeah. Cordelia, it's your turn to ask question. Serum. Oh.
I'm Sriram from NIST. So yeah, we had a Zoom call where we went over some of the some parts of the problem statement, what can be done, what cannot be done. One of the things is like learning the real forwarding path. Like you have a definition of the real forwarding path. Is it included in this? I read through the draft. I don't think I saw that. Real forwarding path, what is the definition?
You mean
the data path.
You mean the definition about between the interdomain and the intradomain?
No. Just think of the interdomain only, what you presented. Just think about that.
Yeah.
And you said that, I mean, you say in your slides that the real forwarding path, the SAV should be based on the real forwarding path. So
yeah.
A definition of that.
Yeah. The real forwarding path means in the data plane, the traffic, the path that the traffic goes through.
Yes. But but in order to be, yeah, then the question becomes, how do you, there are so many possible forwarding paths. That is, I mean, you have the multi-homing, and because of that, there may be I mean, there may be asymmetric routing, and that is what we are all struggling with, right? There is multi-homing, there is asymmetric routing, then there are hidden prefixes, and so on. So when you do have asymmetric routing, it need not be only at the edge of the network. Even in the network, as the data packets moves forward, at each node you can have multiple providers, and you don't know which of those providers the data was sent to. So it seems like it is a difficult thing to pinpoint the actual forwarding path, unless you say that there are all these like paths that are available for the data to propagate, and any of those available paths it could have taken in order to get to the point where you are doing the SAV. So it's hard to pinpoint the actual real forwarding path. You don't know that. All you can know is be able to sort of enumerate and say which are all the possible paths that it could have taken. So that's one comment. So something to keep in mind. Right. And the other thing is that for the provider interface, you pointed out already, and we had this discussion in the Zoom call a couple of months back. You can have, right, like you show there, you can have a good packet and a bad packet can both come on the provider interface, and it is hard to tell which is good and which is bad. You just accept both. So you would have some improper admit. I think that's the problem you're dealing with here. So here something needs to be, we have to be careful maybe. That is why even for the intra-domain, Jared made a comment that section 3 point should be removed, which dealt with the provider interface. Same thing here too, that for the provider interface, no matter like how hard you work on it, what happens in the end is that AS4 for example, AS4 will give the full table, assuming it is all DFZ, it is. So AS4 gives the full table to AS2, and then AS2 pretty much has to accept almost any prefix in the source address coming from AS4. So it's hard to narrow that and say that I would be able to eliminate improper admit. What you have to rely on in this case is that AS4 has to actually depend on AS3 to upgrade and do its own SAV, so that the spoof traffic is stopped at AS3 instead of being allowed to go to AS4. But if it does go to AS4 and AS4 sends it to AS2 on a provider interface, it is very difficult for AS2 to be able to filter that. So there are some of these complexities which probably can be discussed a little bit more in the intra-domain problem statement. I'll be happy to discuss that with you separately.
Sure. Thank you, Sarah. And thank you very much for the comments. For the first comment, I think because various scenarios we have to meet, right? So existing some inter-domain sound mechanisms cannot solve the, can have various problems, maybe improper block or improper meet in the different scenarios, such as asymmetric routing as we analyze in the gap analysis. So yes, we need a solution to a new solution to solve the problems, to face it, also to face these different scenarios, right? Yes, we are. This is a work we are working on. And for the second comment, I think for this scenario, actually we have explicitly stated the setup of this scenario. So, but for the provider interfaces OS to protect to defend against the spoofing traffic, maybe as we analyze Lucio RPF or the ACL-based source-based artificial filtering has their problems. So also, as you analyze, we need a solution, but how to design the solution, we need to carefully and seriously. Thank you.
Okay, thank you.
So we will go to the next participant if there is no any problem.
Hello, good morning, everyone. I'm Nangong from Huawei Technology. Next slide, please. The draft is about intra-domain architecture. In the draft document, we provide some preliminary ideas. In the first version of the document, we received a comment about that we provide too much details. It's not an architecture, actually from our So we made a big update in the version 1 draft. In the draft, we give a high-level design of the architecture. This architecture will collect server-related information from multiple information sources. This information will be used to generate accurate and server rules. And many thanks to the related comments from many people. Next slide, please. Server information source. To generate server rules, we need some kind of information. First is source addresses or source prefixes. And we need to learn all the source addresses, even they are not advertised by root protocols. And the second type of information is incoming directions. First, we need to learn all the real incoming directions. The directions may be incoming interfaces so as to avoid improper block problems. And on the other hand, we need to limit the non-real incoming directions to reduce the improper permit problems. So at least we need to learn all the real incoming directions. And to get this information, existing cell mechanisms and future mechanisms can get them from different information sources. First is configuration. For example, ACL-based filtering can leverage manual configurations to get such information. And Circuitry RPF and Lucio RPF can leverage routing protocols to get the cell-related data. And some newly proposed cell mechanisms like IGP extended cell or BGP extended cell can leverage cell protocols. One of the main features of this architecture is that we include the cell protocol as one of the information source so as to achieve accurate cell. For cell protocols, it's a newly defined information source. It can represent any proposed protocols for source address validation, and it can provide complete or additional information so as to achieve accurate validation. Next, please. This is the architecture. Very simple. We have two entities. On the left, we have source entity. On the right, we have validity entity. The workflow is that the source entity will advertise or send cell-related information through the communication channel to the validation entity. The validation entity will consolidate the cell-related information from different sources and generate cell rules. These cell rules will be used to check the validity of data packets. Next, please. About the source speaker and the validation speaker reside in the two entities. They can be routers or servers. And the speaker actually is an abstracted speaker. It can be a union of multiple speakers. As described previously, we have 3 different sources, so we have different 3 different speakers. First is configuration interface, and the second is routing protocol speakers, and the third is SAO protocol speakers. Of course, SAO protocol speakers may possibly reside in the routing protocol speaker. It can be an extension of routing protocols. Next slide. About the communication channel and messages. Because we have multiple information sources and different speakers, so actually we have multiple channels. Through these channels, these speakers can exchange SAO-related messages. These messages can carry different kind of information. First, we can directly carry SAO rule. The SAO rule will indicate the incoming interfaces of a given prefix. And second, the routing information like existing routing protocols do. And third is forwarding information. We can leverage these messages to advertise the hidden prefixes or some hidden forwarding passes. Yeah. Okay, next, please. SAO agent. SAO agent will get the SAO-related information from the validation speaker. It will consolidate the SAO-related information to generate SAO rules. And we need to deal with one issue, that is there may be some conflicts for given prefix due to multiple information sources. So in such a case, we can set priorities to these sources. The rule with high priority will override the rule with lower priority. If they have the same level of priority, the rule can be merged. Next, please. Connectivity models I just lead 3 kinds of connectivity models. There may be some other models. In the first model, the validation speaker can collect the information from different source speakers. And second, one source speaker can communicate with multiple validation speakers. And the third, the entity can be both source speaker and validation speaker. So the validation speaker can also advertise the data from one source speaker to the other validation speaker. Next, please. A simple conclusion: in the draft, we propose a simple and a preliminary architecture. Is a high-level design. The feature is that we import SAO protocols as one of the SAO information source, so we can generate more accurate SAO rules. It provides such a possibility. And the architecture is applicable to any route-based SAO mechanisms. Here, route-based SAO mechanism means that we check the validity of packets by checking whether the packets arrive the router from the expected incoming interface. All these mechanisms are named as route-based SAO mechanisms in my slides. According to the architecture, we can analyze existing SAO mechanisms and improve validation based on existing mechanisms. And of course, we can design completely new mechanisms. Next, please. This design is very preliminary and has not been completed. It's just a start, and any comments are welcome. And we also welcome collaborators to edit the drafts together. And according to the status of problem statement draft, we will update the draft and provide the first complete design of the architecture. That's all. Thank you.
Thank you. Before Zuyan, just give me a minute and then you can go. I just want to call attention to a couple of things. This is work that is in scope for the working group, but not yet. You're certainly welcome to discuss it on the list because we will need it. But we want to make sure that everybody focuses first on the problems, gaps, and requirements work because that's gating. But it's still very good work. I also want to specifically call out, I appreciate that most of this presentation focused on the inter-element architecture because that's what we can standardize and not on the component architecture, which we don't standardize the insides of routers. So I appreciate it and thank you. Now, Zuyan.
Okay, thank you, Joe. Actually, I agree with your points. I agree with Joe's points. Actually, I also have a question about the cell protocol extension. I noticed in this draft version, you added cell protocol, and it is based on the existing protocol, IGP protocol, and makes some extension, but the protocol extension is out of scope of framework, just as Joe said. So my proposal is that this draft should be focused on the framework. So the requirements, we need to specify the requirements first. And if you have some extension, such as protocol extension, it's about the solution. So the framework specific first, and the technology specific is out of the scope. Okay.
Yeah, thank you.
Okay, thank you.
Yes, actually, the architecture is a high-level design. We will not give detailed solution designs. Yeah, we have the same idea.
Okay,
Yeah.
okay.
Okay, let's go to the next presentation.
So,
no,
okay.
Rudiger put himself. Rudiger, go ahead.
Okay.
I wonder when you're talking about speakers in these systems, I did not see kind of the security of the proposed system. What are the identities? What are the authentication mechanisms used? And potentially, what are the mechanisms supposed to actually enable authorization of authenticated speakers to make statements?
Yeah. Actually, the entity can be a router or a server, and to achieve the speaker, we can leverage existing protocols, maybe routing protocols. So the proposed speaker can be an extension of routing protocols, maybe. Yeah. Actually, we have three kinds of speakers. We can have some protocols for configuration, and this is one of the speaker. And the second, we can leverage existing routing protocol as a speaker. And third one is we can have a new speaker residing in the existing routing protocols. And yeah.
Since you do not want to create security protocols that are actually insecure themselves.
Rudiger, tip the mic up a little. People are having trouble hearing you. Thank you.
Stating actually things like, well, okay, what identities are involved and how are authentication and potentially cryptographic, cryptographic protection of objects probably the second thing, but kind of you actually have to talk about that.
Oh. Oh. Yeah.
Well, okay, that comes from having a large voice anyway. So you really have to talk about identities, authentication, and so on, right from the start in the architecture.
Yeah.
Okay.
And just saying, well, okay, there are things out there that may or may not have a security characteristics. Quite certainly is not sufficient.
Yeah, thanks for your comments. We'll think about your comment. Thank you.
There will be one presentation about the security part later, so I think we can consider to incorporate the security part in the framework.
Jeff, go ahead. And make sure your microphone is turned on.
Testing. Okay, thank you. Jeff Haas. So your presentation sort of dances around this point. Rudiger makes more of the point. If you're looking at routing protocols as a distribution mechanism for this information to supplement and help build the SAV tables, as Rudiger saying, this is itself a security consideration. While I understand the solution spaces are potentially out of scope, I strongly suggest that as part of your in-scope discussion about eventually using routing protocols, talk about the security characteristics of the information carried. And you don't necessarily want routers receiving information that, theoretical example, may be cryptographically signed, so this is safe to use to throw everybody's traffic onto the floor. You don't necessarily want that work actually being done as part of the routing protocol itself, but a solution that implies that this is what is need to be done to carry the information safely in routing means that you have a solution that potentially has difficulties being deployed. Very similar to like reasons we don't see BGP-SEC deployed. The cryptography is an obstacle to the work.
Yeah. Thank you.
Okay. So if there is no any question, we will go to the next presentation.
Okay. Hello, everyone. I'm Lan Chengqin from Tsinghua University. I'm going to introduce the interdomain source address validation subnet architecture. Next. Interdomain SAV is important for mitigating source address spoofing attacks in interdomain networks. However, as described in the problem statement, existing interdomain SAV have limitations in accuracy validation or operational overhead. For example, URPF-related SAV mechanisms have improper block or improper permit problems, and ACL-based SAV mechanisms have high operational overhead problems. To address the limitations, interdomain source address validation subnet architecture provides a framework for developing new interdomain SAV mechanisms. Next. So interdomain subnet architecture aims to enhance accuracy and facilitate partial deployment with low operational overhead. There are 4 design goals. The first goal is accurate SAV at peer and customer interfaces. The AIS with interdomain SAV deployed should accurately learn the valid source addresses that should be permitted at peer and customer interfaces and block packets with other source addresses. The second goal is accurate SAV at provider interfaces. The AIS should accurately learn the invalid source addresses that should be blocked at provider interfaces and permit packets with other source addresses. The third goal is automatic update. The new interdomain solving mechanism should adapt to dynamic networks and asymmetric routing scenario. The last goal is working in partial deployment. The new interdomain solving mechanism should provide protection for the deployed ASs in partial deployment scenario. Next. So we have presented the version 00 in last IETF meeting. In this meeting, different from version 00, which focuses on the specific new solving mechanism. This version 01 focuses on high-level architecture. Specifically, this draft focuses on high-level architecture designs that enable an AS to generate accurate solve rules by using solve-related information from various sources. This draft doesn't include protocol designs or protocol extensions or any detailed solution that should be considered in specific interdomain solving mechanism. Next. So as shown in this figure, the basic idea of interdomain SAVNet architecture is to consolidate solve-related information from multiple sources and generate accurate solve rules based on the solve-related information. There are four main components in the interdomain SAVNet architecture. They are solve-related information sources, solve-information manager, SIM, solve-information base, SIB, and the solve table. Next. I'll first introduce the solve-related information sources in interdomain SAVNet architecture. Next. Solve-related information that specifies the valid incoming interfaces for a source prefix can be learned from three main types of sources. They are manual configuration sources, passive acquired information sources, and active collaboration information sources. The manual configuration sources include solve-related configurations from young command line interface and some protocols such as RTBH and FluSpec. The passive acquired information sources include topological and routing information from routing information base, routing information message, or RPKI, ROA, and SPAR objects. The active collaboration information sources include real forwarding paths transmitted by collaborative messages from other ASs. All sources are optional depending on the availability of the sources and the operational needs. Next. So I'll introduce the SIM. SIM is the core in the interdomain SAVNet architecture. Next. It has two main functions. The first function is to maintain the SIB by consolidating solve-related information collected from multiple sources. The second function is to generate solve rules to fill out the solve table in data plane based on the SIB. Next. So the solve information base SIB contains the collected solve-related information in control plane. Next. Here is a simple example. We can see the topological. We focus on the yellow ASX, and it is connected to 5 ASs. Assume we can collect solve-related information from all sources, and we can get the solve information base for ASX on the left. So we see the data structure of SIB. Each row records the index, the prefix valid incoming interface, the prefix incoming direction, and the corresponding information source. For example, looking at the first row with index 0, it means the solve information learned from collaborative message and routing information message specify interface 1 as the valid incoming interface for source prefix P1. But we also notice that different information sources may specify different incoming interfaces for the same source prefix. For example, looking at the first and second row with index 0 and index 1, we can see the information from collaborative message specifies interface 1 as the only incoming interface for prefix P1. And information from routing information message specify both interface 1 and interface 2 as the incoming interfaces for P1. And RIP specifies interface 2 as the only incoming interface. So next slide. So how to identify the most accurate incoming interfaces from multiple information sources? One principle is that finer-grained information source can help generate more accurate sub-rules. So following this principle, operators are allowed to specify how to use the sub-related information in the SIP by their local configurations, such as defining the priority or granularity for each source and design how to generate the most accurate sub-rule. Next. So the subtable is the data structure in data plane that implements source address validation. Next. So each row in the subtable records the most accurate incoming interfaces for each learned source prefix. As mentioned above, how to use the SIP to generate the subtable is open to the specific new interdomain sub mechanism. Next. So after generating the subtable by checking the source address and the actual incoming interface of each packet against the local subtable, the validated state of each packet can be considered valid, invalid, or unknown. Packets with valid state should be permitted. Packets with invalid state should be blocked. And packets with unknown state can be blocked or permitted according to the sub-configuration. More details about how to use the subtable can be found in another draft. Next. So there are some considerations for the interdomain subnet architecture as well as the possible new interdomain sub mechanisms. Firstly, working in partial deployment, we found some information sources may not provide sub-related information for all source prefixes in partial deploy scenario. For example, IPKI is deploying and the collaborative messages is also depending on the deployment. So new interdomain sub mechanisms must support partial deployment. We also considered the security issues. Using active collaboration information faces the same security threats as those of BGP, including session security threats and content security threats. Existing BGP security mechanisms can be used to secure collaborative protocols, but an independent security mechanism is also needed when some BGP security mechanisms are not widely deployed. Next. So in conclusion, this draft defines the high-level interdomain subnet architecture. It uses sub-related information from multiple sources to generate accurate sub-rules. And this architecture can integrate existing interdomain SAV and also leaves open design space for new SAV mechanisms, including how to select appropriate information sources, how to collect and update the sources information, and how to use the SIP to generate subtables. Next. So we also solicit comments so that we can refine the draft. Many thanks to the helpful revisions, especially thank Igor for his helpful revision suggestions, and he is also the contributor of this draft. And your new comments are welcome. We also seek cooperations. Thank you.
Thank you, Siri.
Can we go to slide 5? I'm Sriram from NIST. So just a little question about the terminology. Passive acquired information. So you're calling BGP or RAIB and ROA and ASPA passive acquired information. Well, BGP is kind of dynamic. The routing changes, and BGP brings you the latest updates regarding the changes in the routing. So in a way, I mean, that is also active. Even ROA and ASPA, as ASS acquire new prefixes, they create new ROAs. They create a new ASPA when they have new provider relationships, for example. So in that sense, I'm just questioning if those are also in a way active, right? And then collaboration information, again, about the terminology. In a way, ROA is collaborating. I mean, when you create ROA, you are collaborating with other ASS, letting them know which prefixes you originate. Yes. Same thing with ASPA. You're letting others know which providers which are your providers, for example. So you are letting people know in a collaborative way. They all are letting each other know collaboratively what are their providers, what are their peering relationships, what are the ASS prefixes they originate from their AS. So in that sense, that's also collaborative information. So I think what you mean by active collaboration information here is that you have tailored messages. I think you are referring to tailored messages that are tailored towards SAV. So just think about that, the jargon, what is an appropriate terminology that you could use.
Okay, we will carefully to take some revision about the the passive or active. All right.
Okay, thank you. Igor?
Thank you very much for that little shout out. One of the, I have a comment, so it's also what Sriram was talking about, collaborative messages. I mean, there is a section about them in the draft that actually specifies what they're supposed to be doing, which is propagate or originate real forwarding path information. So I think the draft would very much benefit from some discussion, maybe in security considerations, maybe elsewhere. Discussion of those messages taking the same data path as the packets are taking, and any sort of concerns that implementations need to be aware of, that in terms of a delay or loss of collaboration, active collaboration information may have an improper block, for example. So it's basically a concern that if we have special messages that are just for SAV, and without them, we may have improper block that really should be highlighted as a security or some other consideration.
Thank you. The security consideration is very important because if using the active collaborative messages, it is transmitted through ASs, and we should confirm the accuracy of these messages.
Igor, if I may, just to confirm what I thought I heard you say, and I'm not sure I understood you. You were talking about the value of paying attention to when the control information flow is congruent with the data flow and taking advantage of that congruence when it applies. Is that what you were talking about?
So I was talking about the risk of data flow and control flow using the same data flow to distribute the control flow, which is subject to both latencies and packet loss, and the problem that happens when this control flow is necessary for avoiding improper block. Because, I mean, thinking of BGP that changes can change any moment, and the second it changes, immediately packet starts flowing. If we're really truly trying to communicate actual forwarding path, as the forwarding path change, the control flow information might not make it before the data makes it to the next hub.
Thank you. Jen?
I noticed that in the interdomain architecture draft and your slides, you mentioned about the subtable, and there's another individual draft which is mainly focused on the subtable. So what's the relationship between these two drafts?
Yeah, so if you want more details about the subtable, you can refer to that draft.
Yeah, I mean, what's the relationship between those two drafts? Is the subtable draft going to be included in architecture or something?
Yes, I introduced the subtable. So as a subtable, how to use it is a part of the whole architecture. So I just introduced the subtable in brief, and how to use it for details is in another individual draft.
Okay.
Okay. Xueyan from ZTE.
You take the microphone.
Okay. Xueyan from
Lean
ZTE.
in. You need to be close to the microphone.
Okay, thank you.
Thank you.
Okay, better. Okay. So also question about the architecture. From this picture, I can find the specific part with the interdomain. Can you tell me the difference and the relationship between the interdomain architecture and the interdomain architecture? Yeah.
Oh, there is some difference. And for example, the intradomain architecture, the components is some different. It's the speaker, the identity, as just said by Gengnan and after you, and the identity is different first. And there are also specific architecture components, such as the sources are different, and the subtable, the usage, and or the collaborative message, and they are also different in intradomain and interdomain networks.
Who? Okay. I wonder whether an explicit consideration actually has to go in for not only addressing incremental deployment, but, well, okay, not the, well, okay, to consider quite actively operation under convergence of the global routing topology. That might actually be a concern that somehow relates to something that Igor was saying, but kind of quite clearly when you are operating in the global internet, you know it is always in convergence. It's never stable. And a kind of one idea addressing that might be to actually actively elaborate on what diagnosis function and logging you would do for, well, okay, it's great you are dropping bad packets, but in a moving system, you may have things that Igor was pointing to where packets are dropped and, well, okay, the convergence goes into a cycle and you have the bad situation all of the time. And it is actually very essential that information about the operational problems get reported in ways that allow operators to actually address the underlying problems. Not thinking about diagnostic and logging in an application like this, straight from the beginning, is just going to create immense operational problems. And we should avoid that.
Thank you. I'd love to hear more operating experience from the community. Thank you.
Okay. Ben, go ahead.
Hi, Ben Madison from Work Online. Rudiger said most of what I was going to say. I think that, okay, so there's a few things. The security properties of this kind of additional set of collaboration mechanisms, I think, need to be explicitly called out in a set of requirements. I think that we all kind of agree that there's, that there's the security properties are important, but I think we actually need to enumerate what those properties have to be in order to be considered valid under this architecture. I also think, and I think this is what Rudiger and Igor were both saying, is there are a whole bunch of really interesting race conditions that I can imagine exists in this kind of a system. I can imagine, for example, the collaborative messages shooting BGP in the head, or BGP shooting the collaborative messages in the head and getting into an endless reconvergence cycle, which I wouldn't want to be the person woken up for that at 3 a.m. I don't know how to get around that. I suspect what might need to happen is you might need to get a bit more specific about what the allowed semantics of the collaborative messages are, beyond what the draft seems to say at the moment is kind of this additional mechanism could exist and it could say some things, and that's left to further work. The third thing I wanted to point out is that I think you need to think about the relative security properties of different, in particular, BGP sessions. We might need to think about how, for example, information learnt on BGP-sec enabled sessions coexists with non-BGP-sec enabled sessions, and there's various examples of that. I think that overall it's kind of stuck in the draft as it reads at the moment is kind of stuck in this weird no man's land between being an actual protocol specification versus being an abstract architecture. I think parts of it read as kind of, actual operational imperatives, and part of it read in this fairly kind of hand wavy, this stuff could exist and this is how it could coexist. I think maybe a good way forward would be to chat to Sriram and Igor about how this coexists with BARSAV, because there's quite a lot of overlap in terms of the mechanisms that are envisaged. And I think that maybe we could find a happy medium between the quite specific protocol requirements of BARSAV and the more general purpose extensible architecture that you've got. I think that maybe proceeding with both in parallel is not productive. A suggestion.
Okay, thank you.
So, okay, let's begin the next part for the additional topic.
This is Michael Huang from Huawei Technology.
Okay.
First of all, I want to do some clarification. The question from Jen: what's the relationship between this subtable draft with previous slides? Actually, we try to jump out the details of how we how the network elements to collaborate with each other to get the subtable generated. But in this draft, we try to stand the point of the view from the whole network. What kind of capability we may miss, in terms of set, mechanisms. So this. First of all, we want to give some kind of background. So why we think a current set mechanism need to be enhanced. So I will not share much details about the URPF and ACO stuff because already shared by the previous day. I want to just give some summary of the gaps. So first of all is about the incentive. One is that current mechanism, we more focused on the outbound traffic filtering. So which means we cannot provide much better, protection from the incoming traffic. So why is that? Because right now the ingress filtering is most focused on the interface-based source prefix allow list. Do we have chance to get another way to do protection from the outside interface? This is the one thing about the incentive. The other I want to emphasize that is that currently we just silent drop, normally common practice, right? So silent drop the packet when we failed to pass the validation. So what if we, this is kind of a waste. When we get some packet that is so spoofy, if we can get some information to the security center, that will help a lot. So why we don't do that, right? Because in this way, we know who is the attack source and who is the target, and even more, we can get some intelligence that to help the security center to tell what happened right now, right? This is the other way I think we will be missed, from current SAV mechanism. And secondly, is about the scenario limitation. You may know that as we all discussed before, that right now the scenario is more focused on the symmetric routing scenarios. So what if the scenario is asymmetric routing? What kind of SAV mechanism we may need in that case? And another thing is that I want to introduce some kind of terms like open connected interface and the closed connected interface. Right now, the interface, we focus on more the close connected interface, like, the outbound interface, right? But for inbound interface, it seems like we don't have so many tools. So this is the two, limitation about the scenarios. The other one is that no matter URPF-based or ACL-based, there are no native source address validation tools, right? So we missed kind of native source address validation, which means we can do better, performance and scalabilities kind of thing. Yeah. Yes. Oh, here.
I think you need a brief introduction for this slide.
Yes. So here's the brief about self-taping abstraction. Actually, it is a lot about the implementation solution in data plane. It's kind of formal abstraction about the self-table. We have, for example, we have 3 modes for self validation. One mode is right now is popular in like interface-based source address prefix allow list. This is one we familiar with. But another two modes we want to introduce is that in the case we cannot get the whole set of the source address, what if we have, block list? I mean, for the given region we know, this source belongs our own, so cannot come outside. Why we don't do block list? And another one is for the specific source address, we know which interface is allowed. So how about we do this way? This is three modes we want to introduce. And also for the action like that, we also can do filtering, but also we can do car, right? And also we can do sampling. So that's it all. Okay, thank you.
Okay, because the time limited, so we'll leave the question on the list. Okay, thank you.
So Libyan, do the real path discovery and SAV Open Playground brief presentation?
Hello, everyone. Can you hear me?
Yes, go ahead.
Good morning. I'm Li Chen from Zhongguanshen Laboratory. Sorry for not being there in Japan today. And today I want to talk about SAV Open Playground and our implementation of the real path discovery protocol. So next slide, please. So basically, we encounter a meta problem in when we are doing research on SAV. The problem is fourfold. First, we witness a lack of reference or starter project for the development of SAV mechanisms, and we cannot find an experimental environment. And we believe visualization and teaching tools is also very much needed by the community to actually promote the deployment of SAV. So basically, please next slide. So basically, we implement SAV to fill the gaps, and SAV can actually do the four things we mentioned in the previous slides. Please next slide. Please next slide. Sorry. So basically, SAV is developed to fill the gaps. SAV is open source, and it has four core components. The SAV reference router, a virtual network manager, and a browser-based visualizer, and a scenario replay tool. So the SAV workflow is actually very simple. So the user will submit their simulation scenarios through a web application, and the backend will spin up containers and virtual networks according to the intended topology and configuration. The containers have a software router and a SAV agent. So each container will emulate a router running SAV, and in all, it will run the user's intended SAV experiment or scenarios. Please, next slide. So let me talk more about what's inside container. So we used BIRD as the base router and implement a SAV agent to encapsulate all the SAV-related procedures and data. And the SAV agent extracts useful information from the BIRD router and use the user-defined SAV mechanism to generate SAV tables. The SAV table are then enforced using IP table entries configured by the SAV agent. So with the SAV agent, BIRD, and the Linux kernel networking stack, the container as a whole will emulate a router running SAV. Please, next slide. So the SAV agent actually makes it easy for us to implement the new SAV mechanisms. Here we use the DSAV framework, which we presented in 2022 in IETF116, and we rename it to the Real Path Discovery Protocol, RPDP. RPDP differs from the other SAV solutions because it's a hop-by-hop protocol that propagates the SAV information. So in this example, the AS1 propagates the prefix P1 to AS4 in a hop-by-hop fashion using RPDP messages. So that AS4 can configure correctly the incoming interfaces of P1. I will not talk more about IPDP in details, and it deserves a separate presentation. So I will only talk about its implementation. Please, next slide. So we extend the BGP implementation of BERT and implement a IPDP protocol speaker so that the SAF agent running IPDP can talk with each other and generate the correct SAF table managers, SAF tables, and then the SAF table manager will implement the SAF rules using IP table entries so that the data plane packets can be correctly permitted or denied based on the SAF results. Next slide. So the virtual network manager is another core component of SAF. As we discussed before, the manager will set up container network for SAF scenarios based on the user input. Please, next slide. So SAFOP also has a visualization and replay tools, and we actually have a short demo, and you are welcome to follow the two links. In the demos, we can show topologies and replay the messages used by the SAF protocols, and finally we can see the generated SAF tables for each router in the network. Please, next slide. So in the future, we intended to implement more SAF mechanisms and more protocol extensions to follow up on the workgroup's charter. We also want to run the SAF agent on more routers, including open source ones like Quagga and commercial routers. We also expect a containerized or plugin based deployment scenario so that the SAF agent can automatically configure the ACL rules based on the chosen SAF mechanism. We actually hope this can promote SAF deployment because in this way, we no longer need to rely on the vendor's implementation of individual SAF technologies. And with that, thank you, and I'm ready to take questions if there's any.
Thanks, Tony. I think this is the basis for the future development of the SAI protocol. So because we have no time for questions, so we will go to the next participant.
Yeah, thank you.
So hello everyone. This is from Tech Mobile. I will be the presenter for me and Changwang from 3C. So next slide, please. So in this meeting, most of people talking about the raw IP. That means the public IP access for the internet service like that. But I will talk about the SRv6 because SRv6 kind of without routing paradigm. So we also understand that there are some kind of security issue that requires source address verification or validation. So I think that is somewhat relevant with this SAVNet work group. So in this slide, we understand the SRv6 in SRv6 the destination address of tunnel can be VPN seed. We propose in using the service seed as source address as well. That means for the L2 or L3 VPN, we can use the VPN seed as source address rather than the interface or loopback address like that. So next we are with the source seed as source address, we can do some kind of verification or validation. The first is we can do the source address spoofing prevention validation. That is we can that is on the next hop of the SRv6 tunnel headend, we can do source address spoofing verification by doing strict URPF. So this is one of the we can do. The other validation we can do is on the tail end of the SRv6 tunnel. We can introduce an SRv6 source verification table, which stores all of the authorized source address and the associated VPN. With this information, we can filter out all of those unauthorized VPN access, allow only legal VPN traffic. So next slide, please. So so we have several use cases. The first use case is for SRv6 to pass through the SRVR, the stateful firewall. As we know that firewall requires the symmetric traffic from both of the forward and backward. That means the destination and source address should be just a turnaround in the forward and backward direction. So in most of the SRv6 implementation today, the source address is using the loopback address, but the destination is kind of VPN seed. So that means the traffic from the forward and backward direction are not symmetric. So traffic will be dropped by the firewall. With the seed as the source address, we can meet the requirement of the firewall that has both direction of the flow has a symmetric address. So that is the first use case. The use case 2 and 3 are for overlay and underlay VPN service respectively. So the idea is to because in SRv6 even for especially for BE mode, it is easy to falsify and destination seed, lets user to access any of the VPN services, even if the VPN not itself. So the idea is to do the VPN verification on the tail end of the SRv6 tunnel, like what I said in the first page. Next page, please. So the consideration, the thing is, if the ICMP come back, if there are some error, so there are already some specification from 86. So I just put it here. So that's all. I think that's all.
So thank you, Yang. I think this draft should be discussed within the Spring Working Group, and later we can think what output for the SAVNet Working Group. Okay.
Yes.
In particular, on the email list in Spring, to see whether Spring thinks this is a good or bad use of this information and so forth. And only after that, we'll see if it's relevant to SAV.
Yeah, thank you.
Sorry, I can't open my camera, so maybe in so maybe
okay.
Okay.
You can
okay.
see.
Can you hear me? Can you see me?
Yeah, we can hear you.
Yeah. Okay. Today my topic is source address validation enhance its security using blockchain. I will talk about it briefly. Next, please. Some rules are generated based on routing information or non-routing information. If the routing information is poisoned by attacker, there will be no way to verify the authenticity of the routing information, and the generated sub rules will be incorrect. The main security threats to sub come from the following areas: RPKI was attacked, wrong AS prefix advertisements, and a malicious router. Next, please. Such as RPKI has a defect of single point of failure, and the whole network may be paralyzed after the attack of high-level CS. So RPKI has a problem on being centralized and temporable. Depending on the centralized trust model, once the authority node is misconfigured or attacked, it raises security issues and is difficult to avoid from the mechanism. Next, please. And the exciting routing protocols cannot guarantee the integrity of ASIP prefix advertisements and cannot authenticate whether the AS advertisement IP prefix authorization is legitimate, causing security events such as origin hijack, traffic eavesdropping, and traffic black holes. And the attacker disguises the malicious route as a peer node, propagating false advertisement message or tampering with legitimate advertisement messages, which will not only destroy the solve function but also affect the entire routing domain. Next, please. So consider about the problem. We think about blockchain as a good solution. Blockchain technology, due to its natural attributes of decentralization, tamper-proof, and traceability, is supported by distributed node authentication and consensus mechanisms, allowing any two nodes in a distributed network to reach an unmediated trust. Another advantage of applying blockchain to Solve is that it can add additional security without changing the BGP protocol, and by using blockchain Solve can be protected in several ways, such as replace RPK, AS prefix advertisement information authentication, malicious router discovery. Next, please. Through resources transaction record and the resource retrieval of blockchain's smart contract technology, the IP address and ASN registration and the allocation information are recorded, and the tracking of their usage is supported, so as to realize the authentication of IP address and ASN network resources, prevent the security threat of prefix hijacking, and avoid the repeated allocation of resources. Next, please. And the blockchain smart contract is used to record the IP address authorization. When AS prefix advertisement is required, the prefix advertisement of source AS can be stored on the blockchain. And store the routing topology relationship in the blockchain. When the AS discovers the malicious advertisement information or the AS through the blockchain verification, the network location of the malicious route can be located in a timely manner. Okay, that's all. Thank you.
Okay, and Joel Halpern, speaking as chair, I want to clarify, arguing about alternatives to SIDR and SIDR path or origin validation or BGP validation are all out of scope for this working group. We're talking about packet source address validation.
Yeah.
Yeah, the charter. This is out of scope. I'm sorry. I mean, I may be sympathetic to the problems they want to address, but it's not the problem for this working group. And we're running rapidly out of time. So Jeff will give you a chance because you walked up to the mic to say one thing, but we're out of time, guys.
Jeff has, and I will keep it short.
Okay.
A way to frame what this solution seems to be looking for is to allow a set of colluding parties to override legitimate resource allocations, to say what I'm going to do or not do from a source validation perspective. If that's not your intent, write that up.
But those questions are for other working groups.
Yeah, but we think about the self mechanism is the self security is very important. So maybe we can use blockchain in self. So we propose this draft. So we propose this draft.
I will also be clear, solutions are much, much later in our charter. Even if this were in scope, it is way premature, and I don't want us spending time arguing about it. But we do not have time for the next, it's 10:29.
Okay, thank you. Bye.
I think the chairs shouldn't have put this on the agenda. I'm sorry.
Can I start? Yeah, okay. This is Wei Jiangcheng from China Mobile, and here we would like to provide some considerations on how to use the subnet feature in operators network. So next page, we would like to raise some new conception. We call that proactive defense network. Next page, please. And the background is that, currently the security for the network of operator, we often use a single point method such as firewall, but it have some obvious problems such as a lack of network level view and make the source tracing difficult, something like that. And when we see the SAV idea, we found that maybe we can set up some solution based on the network so that we can, such as achieve the proactive awareness of the threat or something like that. Next page. So the basic architecture, next page, like SDN architecture, we have the routers which can support subnet basic functions, and we will have a security analysis center that like controller. So the routers can report the threat it sensitive, it got to the analysis center, and then the threat can be analyzed, and finally it can run some policy to protect the network. So the benefit is that we can get the some useful solution, even the subnet is partially deployment, and even the subnet is not so accuracy guarantee. That means that at the beginning, we deploy the subnet, we can get benefit. So the use case, firstly, for operators, we can get the security situation awareness. And the second, for the customer of operator, I think we can provide a security service. Maybe we can give some warning for our customers. In next page. So the third use case, maybe we can do the track source tracing, and the last one, we can optimize the security planning for the entire network of operators. Next page. So for the considerations to deploy the solution, and here we assume that we have a strong server solution already. So phase one, we just focus on the threat awareness based on those server solution. And the phase two, we take the threat elimination actions, but maybe manually. And finally, we can get the automatic proactive defense system, so that at the beginning, when we once deploy the solution, we can get benefit. Next page. Oh, thank you.
There is one similar proposal for the framework. So I think such your program the proposal can be incorporated into the architecture design in future. So
yeah, maybe we can do that. But I think for operator, I hope to provide more considerations from our perspective. So maybe we can detail some solutions here. Yeah, thank you.
So, thank you all person to attend the side meeting. Okay, see you next time.
We should not have.